All right, this is a quick review of Gauss's law we discussed in class today. So we have an integral over a closed surface of electric field vector with a dot product with our dA vector that equals q inside over epsilon naught. So let's apply it to a couple of examples here. So first of all, we have a very big line of charge here, and we'll say that this charge is positive. Okay, therefore, we know we're going to have electric field lines going out from this perpendicular to the line of charge. So then what kind of Gaussian surface can we draw to capture those lines? Best would be to draw a cylinder. Okay, so let me just kind of like draw a circle here, a small circle, and another small circle around this. And then we can imagine the sides of our cylinder going up in this direction like this. Now, what part of this cylinder is going to be exposed to electric field would be the sides and not the ends. And let's give the cylinder a length L. And our integral again over a closed surface of E dot dA again is going to be equal to Q inside over epsilon naught. Now, what about the area here? So we don't really need to take the integral per se. We can just calculate what the area should be for this. What we need to do is think surface area of a cylinder. And if we unravel this cylinder, it's going to look like this. I'm not drawing at the scale, of course. This is length L, and this side's here is going to be the circumference of the circle, so 2 pi r. So the area is going to be these two multiplied by each other. So that takes care of our area, A. So A is going to equal 2 pi RL. Now what about Q inside? Let's call this a linear density, lambda is equal to Q, okay, divided by length L. So what would Q inside equal? Q inside is going to then equal lambda L. So now we can plug this into our equation here. Electric field multiplied by area 2 pi RL, okay, is then going to equal lambda L over epsilon naught. And of course, we'll see that the L's cross off. And our electric field equation for a very long line of charge is going to be lambda divided by 2 pi r epsilon naught. Now let's consider a planar sheet of charge here. Let's make it positive again. So we know that our electric field, one more time, is going to be coming perpendicular upwards. Oops, I didn't draw that very perpendicular, but that's okay. Going downwards also, perpendicular. So we got to think what kind of Gaussian surface would allow us to capture those electric field lines. So let's again think about a cylinder that goes through the sheet. And let's draw little dashed lines. Try to draw that as best as possible. If you can imagine that being a better cylinder than I'm drawing. And of course, it intersects our plane right here like this. Let's just call this area A. We know that that would be area of a circle. And this would be area of a circle, also pi r squared, but let's just call it A, and of course this would be A here also. So we see that our sides of the cylinder are not permeated by electric field, but the two tops. And there are two areas there. So again, let's take a look at our integral. The integral of a closed surface of E dot dA, again, is equal to Q inside over epsilon naught. And again, we don't need to take that integral area. We'll just call it A. And there's actually two A's there. So area, in this case, exposed, is going to be 2A. Now, what about the charge enclosed right here? Well, let's call this a sigma, which is equal to Q over A. It's a charge to area ratio. Then Q inside is going to equal sigma times A. So let's put this into our equation. So we have E times 2A is equal to Q inside, which is sigma A, and then over epsilon naught. And we see that our areas do cross off. Okay, an electric field is equal to sigma divided by 2 epsilon naught. All right, our next example. What about a thin shell of charge? So it's a very thin shell and inside is hollow. Again, what's our goal here? We have the closed integral of E dot dA is going to equal Q inside divided by epsilon naught. Now we need to draw a Gaussian surface. This time I'm going to pick a sphere, so I'm trying to draw a sphere that goes around it. Our thin shell has radius r. We're interested in finding electric field at a distance r away. So this, of course, will be the surface area of a sphere. So area this time is going to equal 4 pi r squared. There you go. Now, what about the Q inside? Well, let's again use sigma. Sigma is equal to charge per area. Okay, so Q inside is equal to sigma times A. What's the surface area of a sphere? The same. So this time Q inside is going to equal sigma times 4 pi. Now let's differentiate. Let's call this one little r squared, and let's make this one a big R squared so we don't get confused. So little r for the actual thin shell and a big R for my Gaussian surface. Okay, plugging this in then, we have E. And we'll multiply that by area of 4 pi r squared is equal to sigma times 4 pi little r squared all over epsilon naught. Okay, we see that our 4 pi's can cross off. So electric field now is going to be equal sigma times little r squared over epsilon naught times big R squared. Okay, now we already kind of sort of use this equation. Okay, I'm going to do something here. If I do E and I multiply the top by 4 pi, and I multiply the bottom by 4 pi, then I'm going to be left with sigma r squared over E naught r squared. So I'm kind of undoing our dividing by 4 pi here. Now 4 pi sigma r squared, okay, we've already said that that's Q inside, right? So this equals Q, the charge of this, okay, over 4 pi epsilon naught r squared. We know this another way, K Q over r squared. So that's our formula that we normally use for an electric field. So what do we mean by that? Well, outside of our hollow sphere here, all of the charge again looks like it comes from the center. So we're just using our KQ over r squared equation like we always did before. Now what about if I'm inside? So if I want to draw my Gaussian surface maybe at this distance here. Well, we see that Q inside is actually 0 because our charge is actually residing out here. Now remember, it looks like it comes from in here, but it really doesn't come from in there. So if I just draw my Gaussian surface inside my hollow metal sphere, there's no charge inside my Gaussian surface. Therefore, our electric field is 0 inside that hollow sphere. And we also know that electric field is 0 inside the actual metal here. So we only see an electric field when we're outside, okay, that hollow metal sphere. All right, lastly, what about a solid sphere? Again, a positive charge of Q. Now remember, the electric field lines are actually coming out. That's something I didn't show on the last one, but remember, this is true for both the sphere and the hollow sphere. Electric field is actually coming out like this. Okay. So what if I'm inside, and let's say I want to draw my Gaussian surface like this at some radius r inside, and I want to capture electric field lines from that. Well, let's see. Let's say that the charge density, okay, for this, okay, does have a rho, and it does depend on r. And let's say that equals some constant b multiplied, okay, by r. So now we need to figure out, okay, what our charge density is going to be. Now this, of course, is equal to Q divided by V. Okay, so that's what that equals. So therefore, I'm going to need an expression for dq this time. So dq is equal to br times dv. Now, what, of course, does dv equal? Well, dv is equal to 4 pi r squared dr. So I'm going to plug that into this equation here. Okay, so dq is equal to br times 4 pi r squared dr. Or dq is equal to 4 pi b multiplied by r cubed dr. Now we're going to, of course, take the integral of this, and we're going to have q is equal to the integral from 0 to r of 4 pi b r cubed dr. All right, now let's write that over here, and let's get our constants outside the integral. So q, and this is going to be q inside our Gaussian surface, is equal to 4 pi b times the integral from 0 to r of r cubed dr. Now, of course, the integral of r cubed is r to the 4th divided by 4. And we're going to put limits of integration of 0 to r there. We know that q inside then, as a result, is going to equal 4 pi b multiplied by r to the 4th divided by 4. Or that's going to equal pi b r to the 4th. So that's what our q inside is going to equal. Now remember, we're always doing the integral for electric field is going to be, of course, the closed integral from E dot dA must always equal q inside divided by epsilon naught. Now, of course, our Gaussian surface still has a 4 pi r squared area to it. Now we have q inside over epsilon naught. So let's complete that expression. I guess I'll do it over here in this space here. So I've got E times 4 pi r squared is equal to pi br to the 4th divided by epsilon naught. And of course, we're going to simplify our r's. This will go down to r squared. So electric field then, and we also have our pi's that can cross off, is then going to equal b times r squared over 4 epsilon naught. Now we're going to notice that inside our sphere, we are going to witness an electric field growing, okay, in terms of a quadratic function. So we expect that graph to be, if I do a little quick graph here, that graph would be something like this for electric field. It's going to grow like this. But once we get outside, then we're just going to be kq over r squared again. So then it'll actually start to decline like this once we get outside. So that's our graph of electric field versus radius r. Now this, of course, is when we're at the actual radius right here. We'll call this r. And then outside r, we're going to see a normal decay because we're back to kq, okay, over r squared equation once again. And that is a quick review of our discussion of Gauss's law from class today.